Yeah. So, okay. So the topic here is like the math behind CAD. And so before we start this topic, so I would like to uh, just briefly about Prescient. So what Prescient is. So we call ourselves a engineering software company. And we say that, okay, we are good at software development and our core competencies in the area of algorithms, mathematics, and engineering. And we love solving complex engineering problems. So that's what Prescient is all about. And we have our clients globally. So we have we have clients in many countries. The team size is now more than 275, and the expertise is like for 20, more than 20. Like we exist now for almost like more than 22 years, and we have ISO 9000, 9001, to 27001, and CMMI certifications. And our offerings are in the field of CACS PLM. So when I say CACS, it is CAD, CAM, CAE, PLM, software development, and KB, that is knowledge-based engineering, and also digital factory solutions. And so this topic of math behind CAD is primarily related to CAD software development. So I'll be talking a subset of that. So if you want to do something in CAD in details, in algorithms, it is kind of important to know maths behind that. So uh, that's what I'll be talking about. So, okay. So now coming back, I think just a second. So, yeah, so before we get into math behind CAD, so this is not working still. I'm just trying to, the mouse is not working, so I'm just trying to get that working. Okay, so yeah, so now there are two things here that when we are talking about math, so first thing is that math is kind of a scary subject. So everybody is kind of averse actually to get into math or something. So that is kind of a common. So I also feel the same. So I'm on your side if you feel math is scary. That's one. So challenge to me here is that keep it very simple, so keep it as simple as possible. That's what I have tried to do. And the challenge from your side is like you just stay awake, so when you get into maths, yeah, so sleep is like possible. So yeah, just be with me. And of course, if you have any questions, please note it down with you, or you can type it out. And at the end of the presentation, I'll talk about those questions. I hope I will be able to answer them. Okay, so first, like CAD. So what is CAD? So we always call this computer-aided design, and we all could have some different various notions about CAD, what CAD should be. But what usually CAD is all about is we create and manipulate geometric models of physical objects on computers. So that is what we do. So CAD is about computers. So there are physical objects in the world, and we want to design them on computers. So we should be able to create their models. So when we create something on computers, we are not actually creating a product. Actually, we are creating a model. So and we should be able to manipulate them. So any CAD engineer knows that they would like to create it and change that model, play with it, modify that. So manipulation is also extremely important when it comes to CAD. So that's what we understand what CAD is. And what is computational geometry? So that is another. So we are actually talking. We are getting into like the subject of computational geometry. So what it is? So basically, I would say that geometry always existed. It existed for so many years, and much before like CAD was there. So, but what happened is that when you wanted to create geometric models on computers, it became kind of important to basically treat the geometry in a different way, so that it becomes easily. Basically, you can create geometric models, easily. You create and manipulate them easily. So, computational geometry is basically subject is about that. Okay, so what is the complexity and scope we are talking about? Like when it comes to CAD. So okay, so this picture has some historical meaning. In 2001, I created a training for computational geometry or geometric modeling. So it involved a lot of mathematics, everything. So at that time, I downloaded some pictures that to show that how complicated the models are, and put it in my presentation. So this particular picture is from that presentation, 2001. So the car was looking so swanky at that time. It still looks the same. It was looking so complex, and it still look the same. So this is the kind of complexity CAD always wanted to handle. And and the scope is like all physical objects which we see around. It is possible that we are able to create models of such things on computers. So that is the complexity and scope which we are talking about. Okay, so and like some more pictures, like of course the planes which we fly are also created on computers. So CAD is should be able to create models of that kind, and it does. Or this is basically a tank, or a crankshaft, or a car bumper. So quite a complex kind of geometries we create using CAD. And or there could be very simple ones. So there's a crate, there is a soap case, some plastic component, some steel component. So so the complexity varies. So it could be a very simple part, or it could be very as complex as aeroplanes, and or a complex car which we just saw. So that's the kind of complexity the CAD should basically address to. And if the CAD wants to create models of this kind, the computational geometry also should be able to support mathematics to that level, so that we can create geometries of this kind. So this is basically the kind of scope CAD or computational geometry has in front of them. So now we know that the CAD usage is like spread across. So aerospace and automotive, like CAD is like used. It's a kind of everyday thing. Heavy engineering, manufacturing, civil architecture, we use 3D CAD. Electronics and electrical systems also use 3D CAD at various places. Medical devices, healthcare sector, and so many others. Actually, I just put 5, but there are so many sectors. They would like to, for example, even the movie industry, films. So they are creating 3D models. So 3D models creation and usage is like there in so many businesses. We already know. Okay, so now, okay, so before we go here, so the thing is, we want to create those very complex, for example, a car. So car is an assembly of so many parts that we know. And the assemblies are again sub-assemblies, consist of sub-assemblies, and then sub-assemblies again sub, and somewhere like we have parts and we have components. So it is important that in any CAD system, we should be able to create those models. And if CAD wants to create those models, the computational geometry should be able to support the creation of those models, those parts. So to discuss this topic, actually, so let's start with a very simple model. Like it's a simple model. It has one surface which is a bit complicated, but others are planar surfaces. So kind of everyday. Still not working. Okay. Okay. So this particular CAD model is basically a collection of so many faces. So this is one of the faces, which we are talking about. Okay, so now, so what we see is that the computational geometry should be able to support in some way, some mathematical way, in some way, a solid of this kind, and it has so many faces as we talked about. So what exactly it has? So suppose I click on that particular model, it is possible in some CAD systems, and we know that that particular face. So we call that as a face. This is a face, the magenta one. And this face has an underlying surface below that. Okay, so that is usually not known to us as a CAD user, but all the faces which we see here has a underlying surface. The underlying surface, I'm calling it as an untrimmed surface, so which is not trimmed. So that is basically untrimmed. So a face has an underlying untrimmed surface, and so there is a video. Okay, so I'm just playing a video here. So we just removed that particular model and just created the face. So the face has an underlying surface. So this is basically a surface which we are talking about. And what is here now? So if you look at it, I'll stop it here. Yeah. So this particular surface has some points here, okay, and they are called as control points. And again, it is possible in many CAD systems to see the control points of a surface. So what we see here is that we have a surface, and surface has some control points. We'll talk about what these control points are and what is their meaning and stuff like that. But if you look at it, here we are just moving those control points and the surface is getting deformed. So what it means is that, as a layman perspective, what we can say is that, so these control points are actually really controlling the shape of the curve, shape of the surface. So, and as the name suggests, that's what the control point means. So there are here like 5 by 4, that 20 control points. And by pulling those, it is possible to change the surface, which we just saw. Okay, so let's recap a little bit. So we are saying that we want to basically support the very complex 3D models, say something like car, and it is basically assembly of so many parts, or so many sub-assembly. The sub-assembly has again so many parts or something like that, and then we have parts, and the parts has so many faces, and the faces has, and if I go to a particular face, then the face has a untrimmed surface below that, and the untrimmed surface is being controlled by some control points. So I just recap like what we saw till now. Okay, so now if surface has control points, then what exactly happens to the curve? And the curve also, do the curve also have have control points? So the answer is yes. So here we are seeing a curve, and which also has control points. So now I have a video here again. So what we did is that, oops, sorry. Yeah. So from the surface, on the top of on the edge, we just extracted the curve out of it. So this is the curve, and we saw that it also have control points. So it does, and if I move the control points, the shape of the curve is changing. So surface had control points, the untrimmed surface. Similarly, the curve also has control points that we can see. So so this is basically just wanted to give a glimpse that what is there. So when we say a CAD part, what exactly lies beneath? So a part has so many faces, and if I go to a face, there is always an untrimmed surface below that. Right? Untrimmed surface has some control points. In that surface, if I want to check a curve, see a curve, or I just draw a curve. A curve will also have control points, and if I move the control points, I'm able to change the shape. So I'm changing the shape of the curve or surface using control points. So that is how actually the premise of this computer geometry looks like has been set. So let's see how somebody came to this particular idea of control points and things of that kind. So okay, so before the advent of CAD, so CAD came quite late, say 80s and 90s. It started becoming very popular. But before that, like the computers came sometime in 40s or 50s. And then you must have seen that the computers pictures of those days, like they were like big cupboards, and IBM was the first company they created computers, and the idea was like, okay, so we have something, and what all we can do now? So we can do some calculations there, but what all we can do? So one idea was definitely like CAE, that is FEM analysis. FEM is a subject you cannot really solve that on the in the notebook, right? So it is quite complicated. So you need something like a computer to basically do the computation. So that was definitely one thing to be done, or one subject for computer. But apart from that, people started thinking about this CAD area. But what was before that? So before CAD, what we all know is that the design used to be represented using only through drawings. So even now, actually, many times design is represented by drawings, but at that time there was no choice. So it was always drawings, and the drawings were like various kinds of like GA drawings, and then detailed part drawings, assembly drawings, and whatnot. So many drawings. And those people who have worked before CAD, they would know that to create a little complex part, you need to create so many drawings, and we can imagine that, and there used to be a lot of complexity. If the part is simple, okay, it's easier to draw, but as it starts becoming complex, freeform shapes especially, the drawings are extremely complex. And it's not one drawing. So for one part, there could be like 30, 40, 50 drawings, drawing sheets, and they will basically have so many sections and so a lot of data. And then people would basically take those drawings and then convert those into prototypes and then create actual components and stuff like that. So it's quite a complex process. And then, so everybody knew. And we all know that automobile especially is like a very core part of economy. And if we can design automotives very quickly, fast, everybody would love that. So people thought that can we basically start thinking that, I'm talking about 50s and 60s, that can we bring this uh, the design business on computers, and then the idea of CAD must have emerged. So, and then people started thinking that how we can do. This is especially, I always like to think like this. So whenever I study a subject, I always like to think what they would have thought. And you always get some information, going back, reading, asking people, and then you understand the situation. The situation must be like this: that there are computers, and computers are definitely becoming faster, and eventually they became cheaper as well. So what all we can do there? So, and the CAD was definitely on the cards. So invention of computers. So what they led to, so people thought that now geometric modeling of parts, if I can do on computers, it's a very lucrative idea. So definitely the complexity of designing and the trouble through which the engineers were going through at that time would be reduced a lot, and there will be a lot of enhancement, improvement in terms of quality of the products and the speed by which we deliver and stuff like that. So everybody thought that, okay, it's a very lucrative idea. Now, so it was evident that if you have an appropriate CAD application, it will just replace the drafting board. So that's what people started thinking about. And it also means that it obviously led to study now how to adapt the geometry so that 3D modeling becomes possible. So geometry was always there, as we said. Always means like maybe 1,000 years or more than that. But can we just use that geometry and just put it and then start creating 3D models? I'm sure somebody must have thought on that lines. And but people soon realized that the current form of geometry has a lot of issues, so that it can become directly applicable to to geometric modeling, and so that we can create CAD softwares using that. So, okay, so again, like going back, if we again go back to 60s and start thinking like how people will think, so they would always think that, okay, what is there in geometry? So what does geometry provide? Okay, so we all know that geometry provides points. So there is a coordinate system, and on the coordinate system, if I have X, Y, Z, then we represent points. So this is just an example of a point. We all know. We all know that it represents lines. So this is basically an equation of line, which we learned in 11th and 12th standard in XY plane. So this is equation of line in XY plane. Then we know this equation of, we know circle has the equation. Again, we learned in 11th standard. Parabola, and the plane, it's a 3D plane. So plane is always 3D, of course. So it has X, Y, Z components in that. So it's an equation of a plane. Then we have sphere and cone and hyperboloid and paraboloid and stuff like that. They all have another complex equations. I didn't put it here. So this was all there in 60s or before that. So people knew that we have all that. And we also had some higher degree surfaces also, complex surfaces, which people thought, okay, they could be used. But there were a lot of problems and challenges in using this geometry just as it is, because we want to create it very easily, and we want to modify also it very easily. So that's one thing which was definitely needed. And you all would remember that while drawing in our first year of engineering, okay, there used to be something called French curve or something, and then we used to use that to draw the free form curves, the way we would like to shape it and all stuff like that. So how do we bring equations of those kinds? They are not fitting anywhere here. So how do you basically create free form curves and free form surfaces? So these were the limitations. So the existing representations were not sufficient, and the issues were like, how do we do the about free-form curves and surfaces? And we need that. So, for example, car bonnet or car hood or doors and fenders and all those things, they are not very simple, straightforward, planar kind of models, right? So they have complex shapes, and we would like to have complex shapes so that they become attractive, they become uh, mm, uh, they take care of air resistance and stuff like that. So a lot of there was like a requirement that we need free form curves and surfaces, and that was not easily can be done using our what was there in the current shape of the geometry. And as I said, like we needed very easy creations and manipulations. So that was another problem. How would you do that? And so so suitable representation of geometric entities became a research field. So same geometric entities, but we can be represented in a different manner so that it can be very easily adaptable to CAD-like situations or geometric modeling like areas. Okay, so there is this guy called Bezier or Bezier in French maybe. So a French guy. So he was working in Renault and engineer. I think he did that in late 60s or 70s or something. So he came up with a curve, and that curve is known as Bezier curve. So okay, so Pierre Bezier he was working in Renault, and he came up with a mathematical form for a curve, and which will be suitable for geometric modeling. So that was our concern, right? So it's not some curvature curve we can just create and put it on the book in a book. It's not like that. We want to create a geometric modeling through such representations. So he came up with a new form of the curve. Yeah. And what was his thought process? So I'm not sure whether it was Bezier's thought process. This could be thought process earlier also. This could be a thing directly on the table also, that we should be able to control it very easily with few points. Uh, so for example, if I draw a curve, the curve has infinite points, right? So I cannot give infinite points to represent my curve. So can I just give few points and it just gives me my shape, the initial shape at least. So the concept of control points can emerge. So as I said that I'm not sure whether this was Bezier's idea or it could be somebody else's idea, but can I have some few control points and then I decide the shape? Okay, so Bezier used that. So this is one question in front of Bezier. The another is that okay, another thing. Suppose I have some few points, and through those points I created a curve. But if the curve is not continuous, it is basically cutting somewhere, or it is not smooth, it is going arbitrary somewhere, or then it is not useful. So we want to create real life components. So real life components are continuous in nature. The curve, the shapes which we want to create are smooth in nature. So we would like the curve should be of that kind. And another thing is, if I'm controlling using few points, then it should be intuitive. Like for example, if there are few points and I created a curve using that. Now, if I pull that point and the curve is modifying somewhere else, then CAD engineer will find a lot of problems. Like I'm changing somewhere here, but things are happening somewhere at a very different location. So it should be very intuitive to the user. So these were the kind of thoughts behind getting into or creating that Bezier curve. Okay, so here is the Bezier curve. I just want to show you first before we talk more about that. Uh, so here are 4 points, and there are 4 control points. So only using 4 control points, this curve has been created. Okay, and if you look at it, if you pull the points, the curve is getting modified. Okay, so let's just play it again. So there are 4 control points here, and just 4 control points. You got the curve. Curve looks very smooth, continuous, of course, and intuitive also. So for example, he's pulling a control point, and we expect that the curve should move accordingly, and it is really happening that way, right? And if you see a curve of this kind in late 60s or early 70s, I'm sure like at the same in the user would like to see. So they would like to see that, okay, I have given few inputs and I'm getting a curve, and at the same time it is behaving the way I would like to see. And this is so naturally the Bezier Curve became extremely popular. And so now let's talk about like what Bezier thought and stuff like that. So how did he envisage this particular Bezier curve? So what we're saying here is that we have three control points. It could be n. Last time in the last example there were four. So for here I have just written three. So for example, I have three control points. Okay. Then what Bezier thought is that, can I have an equation like this? You know. So just stay with me. So the equation is that. So I have a control point P1. So P1 is the first control point. Sure. I will multiply. I'm sorry, somebody's audio is on. So can you please mute it? Okay, so the control point P1, P2, P3 are control points. So to P1, I'm multiplying with some mathematical function F1. Okay, so P2, I'm multiplying with some mathematical function F2. P3, I'm multiplying with some mathematical function F3. Okay, and if I do that, I get my curve. Okay, so this is what Bezier is thinking. Okay, and F1, F2, F3 are some mathematical functions which we have not talked yet, but if I can do that, then I can have a Bezier. Okay, so that's the thought. So now what will happen if you just look at this particular thing? So if I change P1, P will change. If I change P2, P will change. If I change P3, P will change. So by changing P1, P2, P3, I will be able to control my curve. So that was the idea here. Now some people might have got confused, or some people might have a question that P1, P2, P3 are actually points. And can you put points in the equation? So we don't actually, right? So we can't put a point in the equation. So what is this? So it is something like this. So it means that I will put x coordinate in the equation and I will get x coordinate of P. Okay. I will put y coordinate in the equation. I will get y coordinate of P. I will put z coordinates of the control points and I will get z coordinate of P. So this particular equation, this equation is actually not one equation. Actually, there are three equations inside of that. One equation is for x, another equation for y, and for z. So the top equation is a kind of cheating or kind of a small way to represent. In one, just put one equation and the reader has to think that, okay, there are three equations. So it's basically we are keeping less space, and in less space we can actually represent three equations. That's all. But we need to remember that whenever we are saying P1, P2, P3, actually in equation, actually there are always three equations: one for x, another for y, another for z. So this is what he thought about. Now, okay, so far so good. Now the thing is that we need to know what is F1, what is F2, what is F3, and then only we can get a curve like that, which we just saw on the last slide. I hope you all are with me. Yeah. So again, let's go back to, we are in 60s and 70s. We are with Bezier. Bezier is doing it for us, and we are sitting in front of him. So at that, I'm sure he must be thinking that what are the mathematical functions I have? What are the choices we have? So we know that we have algebraic functions. So this is basically a polynomial function, which is a very even special form of algebraic. Algebraic means like if there's a square root of x or cube root of x or whatever, they also call algebraic functions. So we have algebraic functions, we have trigonometry functions of sine, cos, tan, and numerous combinations of them. We have logarithmic functions and exponential functions and stuff like that. So these were the choices, to make a choice to create our curve equation. So what he thought? Okay, so this is the equation we are talking about. P1, P2, P3, three control points, and F1, F2. We want to decide what is F1, F2, and F3. So what Bezier chose, he chose polynomial functions. Okay, so there are reasons like why polynomial and why not some others. One simple answer is that, for example, let's consider sine function, sine x. So sine x is always lies in between -1 to 1. Okay, but we want to create real life car, so, and then we need to do a lot of jugglery basically to make sure that we go beyond that. And if sine becomes 1 upon sine x, then it is not in between -1 to 1, rather it is more than 1 and less than -1. If the tan comes in, it can become infinite, or something like that. So the kind of issues we will get into are not the real life issues. We want to design parts which are a few meters. We are not designing anything in kilometers. Maybe right now we are, but or we can. There is no problem in designing kilometers also. But definitely we are not. We don't want to go into the infinity kind of a thing. Nothing intergalactic happening here. So we want real life components to be made on CAD. So the algebraic or the polynomial functions really fitted so well, and it did not bring further complications, which, for example, sine and log and other functions would bring in. So he chose polynomial functions. Okay, so let's go to the next. Okay, again, some recap again. Okay, so we started that we want to design the real life car, for example, on the computers, and we know that car has so many parts, so many assemblies. In those assemblies, there are so many sub-assemblies. In those sub-assemblies, there are so many parts. If I consider a part will have so many faces. Okay, now I want to design the faces. So every face will be, and I will use curves also to design those faces and stuff like that. So curves and surfaces should be easy to create, easy to manipulate. To easily create and easily manipulate, we are saying that can I give some few control points and I start making my curve on my surface. Okay, and how to create that with few points? How can I create a curve? And that is where Bezier is coming in, and he's talking about the equations. Just a recap, we're coming from there and we are coming here now up to Bezier equations. Okay, so this is basically a Bezier equation. Okay, we'll go into details a lot later on. Okay, I still have trouble with my computer mouse, but yeah. So I'll just play this video. So here in this case, there are P1 and P2. There are two control points only, and I'm getting a line here, so which is good. So I've given 2 points, and then Bezier equation is giving me a line here. Okay, and now if you look at it, to P1 we have multiplied by 1 minus t, and P2 we have multiplied. The function which we're talking about, the mathematical function which will multiply to P1, here it is 1 minus t, and to P2 it is t. Okay, so these are the functions Bezier chose. So how did it come to these functions and all? We'll just talk about, but they're very simple functions, right? 1 minus t. Now the next question will come in your mind. We talked about x, y, z. What is this t now? Okay, what is it? So okay, so we'll just stay with this t. Okay, I can talk about this t right away. So the thing is, if the t varies from, let's say, 0 to 1. Okay, so what happens when t is 0? You get something as a p. If t becomes 0.1, you will get some different p. If t becomes 0.2, you'll get another p. If t becomes 0.3, 0.4, 0.5, like that. So what is happening that if I change my t, actually I'm getting so many points, and those points are nothing but the points on this particular curve, which is a line. So t represents the locus of this line. All the points on this particular line are corresponding to some value of t. And if t is 0, you are at P1. When t becomes 1, you are at P2. And when t is in between, you are somewhere in between. So using t, we are actually creating this particular curve. Okay, so t is basically a parameter, and that is why, and basically it is basically a polynomial in a parametric form. That's what we call it. So t is a parameter, and using t, because of t, we are able to basically trace the entire line. Okay, so now this is for 2 control points. Now what happens when there are 3 control points? Like now, so this is basically another video for 3 control points. So I got a different curve now. It is not a straight line, of course. It has a curvature, and again, by changing the control points, I'm able to change my shape. And now, if you look at the equation here, there is a square coming. In the first equation there was no square. Now the square has come. So what we say is that the first equation was a linear equation. The second equation is a quadratic equation. So it's a degree 2 equation. So with 3 control points, I'm getting a degree 2 equation, and that is why I'm getting this kind of a curvature. Okay. Now what happens with 4 control points? The 4 control point has a even complicated curve. So it has even better shape or a little complex shape. Again, the same thing, by changing the control points, I'm able to change my curve. So if you look at it, the mathematical functions which talked about are changing. For 2 control points, they were different. For 3 control points, they are different. For 4 control points, they are different. And every time the degree of the curve is increasing. So earlier the degree was 1 for the line. For the when three control points were there, the degree became 2. Now the degree has become 3. So as you go on control points, the degree is increasing, and I'm getting a complicated curve here. So now using this curve looks familiar to a CAD engineer. Now I don't have to use that French curve to create my complex shape. I can use these control points, and I can start creating my freeform curves and stuff like that. So looks like a very happy situation. I can do Bezier represents a straight line also, a quadratic curve also, a complex 3-degree curve also, or even complex also. So all these things are possible now with Bezier. Okay, so we just talked about the parametric form. So now what happens? My x, y, and z, all these values, my curve x, y, z, or any point is now function of t. Okay, and I just change t, I get x, y, z. So if I become t equal to 0.1, so at 0.1 I will calculate x. I'll with t equal to 0.1 again I'll calculate y and z also, and then I can get my x, y, z point on that particular curve in the space. So this is basically the parametric form which he used. Okay. Another way to show the parametric form. So what happens is that it just traces the curve. As you change the t equal to 0 to t equal to 1, you just keep pulling the t. Actually, it just traces the curve when you put those into the equations. So that's basically a parametric form. So Bezier chose polynomial with parametric form. So okay, so yeah, so okay, we know that for so we talked about this. So for 2 control points, this equation, 3 control point, this equation, 4 control point, this equation, and stuff like that. Okay. Now you might ask a question that now suppose I have 50 control points, then what happens? Who is going to give me these equations? So am I going to remember all that, write it somewhere? What is happening here? And how Bezier is basically deriving every time I just change the number of control points, he's giving me new equations. So how is he arriving at those particular equations? So if you are having those kind of questions, like very right questions. So Bezier actually the question is written like this, okay, and this is a kind of a lot of scary things have come here, and that is why I was keeping this away. So it scared me when I saw this first or something. But remember, this sigma basically is a summation, okay, and this b is basically the function which we talked about, and p are my control points. So basically summation of the function into control point plus function plus control point, function plus control point, like that. Okay, so let's not worry about the complexity of this particular thing. So just wanted to tell you that the right side equation here, if I put n equal to 1, I get the first equation. In the right side, if I put n equal to 2, I get the second equation. If I put n equal to 3, I get the third equation, like that. So Bezier basically came up with this right hand side thing, and using that you can just create, for example, my curve has 13 control points, and I want to create a Bezier curve. Easy. So put n equal to 13 and solve all this, and you'll get an equation like that, what we are seeing on the left side, and that is your Bezier curve equation. Okay. So don't worry about the right side. It looks scary, and but the good part is that if I put value of n, it is giving me very simple looking equation. So that's what the Bezier equation are doing for us. Okay, another interesting thing. So all these functions which I talked about, so this 1 minus t or 1 minus t square, 1 minus t cube are actually this b things. The b things are here are giving me those functions, and Bezier did not create those functions. So the mathematician Bernstein, he had written these polynomials. They are called as Bernstein polynomials. So he used Bernstein polynomials and control point idea, and combined them together and created Bezier curve. Okay, and you cannot have actually. There are some more restrictions that the kind of functions you can choose. Okay, and Bernstein polynomial satisfies that. I don't. Let's not get into that. But point is that you can't have any kind of polynomial equations. They need to be in certain way, and Bernstein polynomial was satisfying those criteria. and using that, Bezier created these equations. This particular equation. So no new mathematics was created here. It is just a rearrangement of maths here. Okay. So again. So again, we can just have a look at this Bezier curve. So the same video. So if I pull the control points, the curve is appropriately getting pulled and pushed. So one thing is that it is giving me a control. So control is like intuitive. Curve is also very smooth, everything nice. But there are some issues also here. Yeah. So there are some issues also here. Somebody's mic is on. Somebody's mic is on. Yeah. So so if you look at this, okay, let me stop somewhere. Sorry. Yeah. So I just stopped the video. See what happened at the second control point, I started moving upwards. But if you look at the Bezier curve, the original curve was black one, and the yellow one is the new one, which has been created because of the movement of the control point. And but if you can see, I just moved one control point, but actually it is modifying the entire curve. Except the endpoints, all the points are getting modified. Okay, now imagine that you are designing a car bonnet, say for example, and you created some curve, and using that curve, you are creating a car bonnet, and you are giving a shape. And now what happens is that you have decided a shape at certain, say in the front side, and now on the back side you are deciding the shape. But if you start changing the control points here, it will change my earlier shape also. So this is my problem. So what Bezier does not offer is a local control. So if I change something, it changes almost everything except the endpoints. So it changes the entire curve. So that is a problem, and I cannot have a local control. So that was the first Bezier problem, Bezier issue. The second issue is this, that you might have realized that suppose I want to create a complicated curve, then more and more complicated curve I create, what I can say, more and more complicated curve I create, the degree of the curve is bound to increase. So when I created 2 points, degree was 1. When I used 3 points, degree was 2. When I used 4 control points, degree was 3. Now suppose I want to create a very long curve, complicated curve, and if I choose 50 control points, the degree will be 49, and that is a very complex curve. And it will have lots of wiggles also. To manage those wiggles is not easy thing. To control such curve is not easy thing, and that is not something CAD engineer would like to see. So they would like to have a local control. So Bezier had these kind of limitations. So new curve was thought somewhere in 70s again. If I'm not wrong, maybe 74 or something. I could be wrong. And that is they call B-spline curve. So we just talked about the Bezier curve limitation. So they have limitations. So their degree increases with the number of control points. They lack the local control. So they envisage the B-spline curve. So B-spline curve has, I don't have an equation here. It is even scarier than the Bezier equation, so let's not get into that. But the concept is similar. There are control points, and multiply those control points with some functions, and you get B-spline curve. Actually, what B-spline curve is really mathematically is basically assemblage of Bezier curves. So, for example, you can have a long B-spline curve. It might have 50 control points, but degree can be still 3 or 4. And now what happens is that it will have so many spans. So every span is actually a Bezier curve. So, and all the spans are connected to each other. It's very smooth connectivity is there. And now what happens is that if I change some control points here, the spans here get changed, but not here. So I start getting a local control. Okay, so the degree problem is gone. Local control has come up. So B-spline curve kind of became now a new standard to represent my curves. Bezier is not vanished, of course, so because every span in the B-spline curve is basically a Bezier curve. So, and you can always have a Bezier curve as well. So you can say the B-spline is a generalized version of a curve for a CAD user. Okay. good, but it has still some problems. Okay, the problem is that now, okay, using B-spline curve, I can create that bonnet thing, and I can create so many complex geometries, no problem. But I also have circles and ellipse and all those things. So can B-spline support circle and ellipse, or it doesn't? Okay, it can do lots of complex things, but it cannot basically represent a circle. The problem. So, so then a solution came up, and what they started calling is that rational B-splines. So B-splines, but which are rational. So forget like what the rational thing is, but B-spline became a little complicated, became rational, so that it can start supporting circle also, ellipse also the bonnet, also the hood, also the door, those kinds of curves. So, and again, there is something called non-uniform rational B-spline. So still more complexity. Still, it can do some curve which are somewhere in the corner, but we will be able to do all kinds of curves now, whatever we need. But NURBS, or non-uniform rational B-splines, are basically more generalization of rational B-splines. Rational B-splines are generalization of B-splines. B-splines are assemblage of Bezier curve. Bezier curve means control points and some functions. So that particular theme remains the same. Okay, so as I said, like they are further generalization and they overcome the limitations and things like that. Okay, so that's that. So okay, all the curves which we generally see in the CAD are represented using NURBS. Okay, so we talked about curves, but what about surfaces? So finally, we are not interested in curves. We are interested in surfaces. Bonnet or hood is a surface. Car door is a surface. They are not really just curves. So equations. So luckily, so whatever we have developed so far, mathematics, the equations of surfaces are very similar to equation of curves. So thank you so much, Bezier, or all those people. So in the curve, we had one parameter t. So by changing t, we could trace the curve. Now here we have two parameters. One is u, another is v. Okay. So by changing u or changing v, I can basically trace my surface now. So by changing t, I was tracing my entire curve, but now by changing u and v, I can trace the entire surface. Okay. So the curve has a control polygon. So which we saw, like there are 4 control points, and they're kind of a polygon. So curve has a control polygon, and in that control polygon, you have your curve. Surface has control net. Okay. So what does it mean? So something like this. So this is basically a surface, and it has a control net. Okay. So, and again, these are control points, and I can just pick up control point and start pulling it, and I can see that my surface is changing. Okay, so likewise, as we had B-spline Bezier curves, similarly we have Bezier surface, we have B-spline curve, we have B-spline surface, we have NURBS curve, NURBS surface. So similarly, now earlier it was just one parameter, here now 2 parameters, and because of the 2 parameters, the shape is like it's not a rectangle, but of course it always has a 4 boundaries. So surface always has a 4 boundaries because of it moves in 2 directions. It moves in u direction also. It moves in v direction also, and so it always comes with 4 boundaries. Okay. So okay, the same mathematical representation which we talked about now is getting extended to surface very easily. Again, I'm not putting equations here. Again, they are very scary, so let's not worry about that. But we understand like what they would mean and what they are representing. Okay, so this is surface control. Now coming back to our problem. So all this mathematics, all this jugglery, we are doing it to solve CAD problems. We want to basically create CAD models. Okay, so but CAD surfaces are not necessarily have 4 boundaries, right? So 4 boundaries is basically the mathematics is giving us. But that is not we want. We want I can have a face with various kinds of boundaries, something like this. Okay, so this is my face. This could be my face of a particular solid. Okay, and it has the outer boundary, the green thing I'm talking about, the outer boundary, and there could be some inner boundaries. Inner boundaries are my holes. Outer boundaries basically boundary of those that particular face. And this is definitely not a 4-sided boundary, 4-sided face. So what do we do now? NURBS and whatever mathematics we talked about is all talking about 2 by 2. They're always talking about. I mean, the 4 boundaries limitation is there. Now, what should we do here? So what they say is that this is how actually the faces are created. So faces are always trimmed surfaces. So if you remember, to start with, I showed you one face, and then I showed you there is a underlying surface. Okay, so every face has an underlying surface. So this particular face also has an underlying surface, which is gray now. And on that underlying, so underlying surface is like, it could be a Bezier surface or B-spline surface. It will have mathematical equations, which we talked about. And on that surface, we have a trimming boundary. So this boundary actually runs, boundary is another curve, and again, that curve again could be Bezier or B-spline curve. Now this curve actually runs on top of the surface. And we say that this outer boundary means my boundary of the face. Okay, so there is no mathematics here, just a topological information. It says that, okay, I have this particular surface which has a B-spline equation, and now there is an outer boundary. The outer boundary says that all the points which are inside our face, all the points are outside, I'm not interested. Okay, now there is inner boundaries also, there are holes also. So what holes are saying that all the surface points which are lying inside that particular loop, inner boundary, I'm not interested, that is hole. Okay, outside, I'm interested. So by this logical information, I'm actually creating the face information. So face doesn't have a mathematical equation. Surface has a mathematical equation. Face doesn't. Face has, on top of mathematically defined surface, on top of that, there are trimming boundaries, outer boundaries and inner boundaries. And using that outer boundaries and inner boundaries, I'm defining my faces. Okay, so again, coming back to the CAD model which we talked about. So now this particular solid, okay, what is that? It has so many faces, okay, and all these faces are connected. So we talked about surface, we talked about face, but now there is additional thing here. There are two different surfaces and they are connected to each other. So what about that? Somebody should know that, okay, who is connected to whom. So that's the next remaining problem, So here we have selected some two faces, the top face and the magenta face, and so they are here. So now what happens is that there are two connected faces. They are sharing a boundary here. Okay, the black is sharing a boundary. They're sharing a boundary here. And what actually happens is something like this, that the top face will have some underlying surface. And on that underlying surface, there is a trimming boundary. On the vertical face, the magenta face also has an underlying surface. On that underlying surface, there is a trimming boundary. And in that trimming boundary, there is some portion that these two guys are sharing. And this information is kind of kept inside. And this information tells that who is connected to whom and stuff like that. And then but now I have all the information to create a solid. See, now if I want to create this particular solid, see, now there are 6 faces. So every face will have some surface below. Every face will have a trimming boundary. And the trimming boundaries some portion of my trimming boundary will say that this portion is connected to that face, this portion is connected to that face, this portion is connected to that face. Now with all this information, actually, I can represent my model. Okay, so okay, so again, recap everything. Okay, so we are talking about creating big cars, and then big cars will have sub-assemblies, and then again sub-assemblies, and then some parts. The parts are of this nature, and the parts will have faces. The faces will have underlying surfaces. Underlying surfaces will have control points so that they can be controlled, and the mathematical equations we talked about. But the underlying surfaces are always four-sided. My surfaces may not be four-sided, so I need to have a trimming boundaries, so I can create a face. But one face doesn't mean everything. The face is connected to some other faces, so I need the connectivity information. So I keep the connectivity information, and by doing that, I create my model. So all this information together means model, which is below, which whatever we are seeing inside, the software is actually having all this information behind. Okay, so yeah, so that's what our model was. Yeah. So as we talked about, the connected faces are the trim faces, and they're sharing common trimming edges. And you might have heard this word. This is called as boundary representation, or B-rep. So they say that, okay, this particular CAD software supports B-rep. So it supports B-rep means it does all this. Okay. So okay. So now yeah. So this is basically a car dashboard, right? And now if you look at it, it has so many faces. And now you know that every face will have underlying surface, every face will have trimming boundaries. There could be outer trimming boundaries. There could be some could have some inner trimming boundaries, which are holes, and they will have some connectivity information. And using that, we have created this model, and we call this a surface model because this is not a solid. The edges below or the edges on the side are free edges. They are not connected to anywhere. So this is basically a surface model. So this is not a solid. Okay, and but using the same VREP, I can basically create this particular surface model. Sometimes the whole thing could be just connected to each other. So here, what has happened is that now this is a model again, engine block. It has again so many faces. Again, faces will have underlying surfaces. They will have trimming boundaries. They will have connectivity information. The difference between the earlier model and this model was there is no free edge, and there are no self intersections also. And then by doing that, we can say that this is a solid, and of course some more information, and then we can conclude that, oh, this is definitely a solid. So solid and surface model, not much of a difference. Only difference is that everything is connected here, and it basically closes a volume. There are some free edges, but the underlying representation. So whenever you see CAD on your screen or any 3D model on your screen like that, so now you can say that, okay, it has so many faces, means that every face will have some underlying surface. Underlying surface will have some control points, some degree or something. An underlying surface will always have four boundaries, but my face may not have four boundaries. It can have a complicated trimming edge. It can have some holes, and every face has a connectivity information. So I'm connected to this guy, I'm connected to that guy, like that, and all this information in the entirety makes the model inside. So thank you so much. So this is what I wanted to cover. By keeping mass as low as possible, as minimum as possible, but wanted to give a glimpse that what exactly lies beneath, what is exactly when I see a CAD model, what is there inside. So thank you so much. And if you have any questions, so please go ahead and ask.
Yeah, thank you, Pravin sir, for this insightful presentation. So if anyone is having question, they can type that in Q&A box.
I think Subir has a question. Hey, Subir, how are you?
Yeah, how are you, Pravin? Yeah,
I'm good. I'm good. I'm good.
so
Yeah.
actually, I remember that you guys have developed a kernel,
Right.
and I was expecting you will be touch upon that.
No, this is a generic talk, like.
Okay. So that is the ultimate product of this discussion.
Yeah, but that's a separate. So this is basically, we are talking about mathematics. We are talking about what goes inside any CAD model, not necessarily what we have developed, but anywhere, like.
But those mathematics are actually ultimately implemented in those kernels, right?
Yeah, yeah, you're right. Yeah.
Okay. But anyway, so good summary of the things, but actually I don't know who are the attendees, but if somebody wants to learn those mathematics, that will be give a idea that what kind of things are supposed to be learned if they want to jump into CAD customization or development. So yeah, they can get a good idea.
Right.
Thank you for arranging this.
Thank you.
I will talk to you separately. Oh,
Yeah. We can.
Okay, thank you.
I can see somebody has raised the hand. I don't know.
Yeah, Sharjit here. Am I audible?
Yeah. Is it? Can I repeat your name, sir? Sorry.
Sharjit.
Sharjit. Yeah. Sharjit. Yeah. Okay.
Yeah.
Yeah.
So thanks, Praveen. It was an awesome session. I really could go back to the old days where, like, I was trying to learn the fundamentals of CAD, and it was, very interesting. But what has happened these days is, like, we have lost a lot of touch in the newer technologies that are coming up in CAD. Say, for example, in the solid edge, something called synchronous technology, right? Where push and pull of faces, and like kind of hybrid models where it is not just BREP always. The underlying data structure stores the data in many ways, and it allows you to manipulate CAD in a much controlled way. And along with that, also the generative design, which is becoming popular these days. So, what kind of geometrical data structures are used where this topology optimization and design in generative methodology is done? Can you please
Yeah.
touch base upon that?
Okay. So here we talked about Bezier, B-splines, and B-rep model, which is basically a must whenever you are designing a CAD products, like we talked about car or something. Now there are some other representations which are like faceted model. So faceted model is where you are creating so many small triangles or small facets and creating a mesh out of it, and then and that they might be using those for the generative models, or they might be using primarily this. But at the end of the day, eventually they will have to create a B-spline and Bezier, the CAD model which we talked about. So whatever we talked about right now becomes the basis, and on top of that, many algorithms are written. Okay, there could be a faceted model kind of representation coming somewhere, but most of the times, finally, when you are creating a very high quality product, you have to come back to NURBS below. At the top, they might be showing some push pulls and some more controls, and there are some algorithms somewhere. But at the end of it, at the fundamental level, at the plinth level, uh, at the ground level, they will be B-spline and NURBS models.
Okay, so you mean that the B-spline, I mean the B-rep model per se is to stay here no matter what level of
Oh yes, 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 yes.
yeah.
So all these are algorithms written on top of that.
Understood. But if we look at the way that we can generate mesh or say triangulated models out of BREF, that direction is pretty easy because all you have to do is tessellate and generate the mesh out of it. But if you look at the reverse way, means once you get into a mesh and you manipulate and achieve a shape, then mapping it back to the BREF is much more difficult, right?
Of course, yes, it is difficult and it is complicated. Yeah, so we have worked a lot in that area in creation. But yeah, so but apart from that, but finally, see the faceted model. If you go and make an actual model as a physical model, it will not look continuous and it will not have that kind of shape which we would like to see. You don't want some arbitrary. Mm, no. You don't want some sharp edges somewhere, even
Right,
if they are
right.
small, you don't want. You want very smooth kind of curvature, continuous kind of surfaces. So for that reason, you need to come back to nerves.
BREF. Got it. Got it. Yeah. Thanks, Pravin.
Thank you. Thank you, Shaljit. Hello.
So if anyone having question, they can unmute the mic and ask the question.
Hello. Hello. Am I
Oh,
audible?
yeah, go ahead.
Sir, yeah, you were discussing about the curves that all these curves they lies within the convex region, right?
Yeah.
Yeah. So how that convex region is identified?
No. See, the thing is, we gave some control points. Okay, and the
Yes.
control points makes a control polygon. And our curve lies inside that. And why it lies lies inside that? That is because of the way the Bernstein polynomials have been formed. So there is a reason why they become like that. So some more mathematics there. But the thing is, the Bernstein polynomials always have a value that ranges between 0 to 1. Okay, and sum of all those functions is always 1. So these are the constraints which I didn't talk about because we will get into some detailed level mathematics. So because of those kind of properties of the Bernstein polynomial function, your curve always lies inside the control polygon which we talked about, and which is a good thing, right? So because a user drew like that and the curve is following that, so curve is not going anywhere. So I just drew 4 lines, 4 points. I just give 4 points and curve is going anywhere in space is not intuitive. So by having these properties, the curve is lying inside the convexal
Yes.
region, the convexal region of that in that polygon.
Yes, but yeah, I was means interesting about in the fact that we can say that the curve can intersect itself, right? Curve can cross itself.
Curve can cross itself. Yeah.
So what will be the convex region for that curve?
Okay, so coming back to this discussion, I did not get into the convex hull. So just for everybody's sake, I'm saying it just means that you have 4 points, okay, or 4 points or 5 points, whatever control points you have. So on that control point, just put a rubber band, for example, okay. And so what will happen is all your control points will be within that rubber band region. So that is called as a convex hull. And because of the Bernstein polynomial, because of very peculiar properties of Bernstein polynomial, our curve remains inside that. And it could be self-intersecting inside, depending on how you put your control points. So if you're putting your control points like crossing each other, I mean, first point here, second here, third here, fourth here, curve will also cross each other. Curve will also cross itself.
Yeah, thank you.
Yeah, Sohan, yeah, you wanted to ask something. Hello, Sohan. Sorry. I can see Sohan raising hand, so.
Any question?
I hope the mathematics didn't scare. It created interest rather than scaring it.
Yes.
That was the intention of the whole exercise.
So thank you for this amazing session. Sir, thank you everyone for joining this today's webinar. I hope you learned more about the elements of CAD/CAM software development. Actually, if you have any question, feel free to ask. You can mail us or you can call us on our numbers given.
Yeah, I
thank
think
you.
there is a question coming. Sachin, can you just wait? There is a question coming from Sohan. Actually, his mic is not working. Okay. So Sohan, can you are you typing it out or whatever? Yeah, I think he is. I wanted to ask that as a beginner in software development. Okay, reading his comment. Okay. Okay, he's saying that where should we start looking for as a new engineer, no? In maths? How do you start learning maths or something? Yeah, so depending on where you are working. So if you're really working in geometry and that area, so yeah, so we need to start learning that part of geometry. So for example, if you're getting into maths, the algorithms which Subir was talking about, then it may be necessary to even start with like vectors and matrices, and of course coordinate geometry and this Bezier B-spline which we talked about. So, yeah. But I always felt that mathematics is a very interesting subject, and even if you're not in that field working, it is possible to go back and refine our understanding. It's very interesting, very pleasing also when we start understanding like whatever we learned in colleges, but did not make a sense out of that, and now we can make sense out of that. So that's how actually I look at mathematics. Yeah. So yeah, is there any question, or if it is not, then we can start. Yes, Sachin, no question, I think. So,
Yeah. Actually, thank you, Pravin sir, for your valuable time. Thank you everyone for joining today's webinar.
thank you so much. Thanks everybody.
Thank you.
Thank you.